So here we're looking at applying some calculations to a portfolio. So we're really treading on the toes of portfolio management, which comes later on in the curriculum, but we're looking at some core key calculations which essentially look at what happens when we combine assets together in a portfolio. So portfolio mathematics, it's called. Here's your hit list, relatively short list, this one. As I say, we're going to look at what happens when we combine assets together. We need to be able to do calculations for when we combine 2 or 3 assets into a portfolio. All right. And we also need to think about calculating covariance when we're given joint probabilities as well. So a joint probability, that's the formal name for an AND probability. So if you like, the probability that asset A returns a certain amount and asset B returns a certain amount at the same time. That's what joint probabilities are, you'll remember. And then we meet the most important distribution for your level 1 quants, and usually the most important distribution, period, and that is the normal distribution. Okay, so the normal distribution is often assumed, rightly or wrongly. It's often assumed in mathematical modeling. We've already briefly introduced it, where we've described it as a symmetrical bell curve. We don't need to worry about the mathematical definition of it, but here we're going to start using it. So we're going to start thinking about the properties of the normal distribution and how when we go a certain distance away from the mean, we capture a certain amount of observations. That's what's called Z values when we think about these distances away from the mean. Okay, without further ado then, let's start with this first bullet point on the hit list, and that is calculating the expected return and the variance of a portfolio of assets. We'll start off looking at a portfolio of 2 assets when we think about what we do. So let's assume we've got 2 assets in the portfolio, asset A and asset B. Relatively straightforward terminology here. You know, the weight of asset A in the portfolio is WA. The weight of asset B in the portfolio is WB. There's only 2 assets. The expected return of asset A is given by that, and the expected return of asset B is given by that. So now the key message that should come across here is that returns are very well behaved. You just take a weighted average of returns to get the portfolio expected return when you combine A and B in this way. Okay, so we'll do an example in a moment, but returns, they always behave themselves. They're never a troublemaker. All right, you just weight them according to their weight in the portfolio and you're done. All right. Just be careful though with risk, standard deviation and variance, because you don't just linearly combine in that way. You don't just take a weighted average in that way that we did for returns. And the reason for that is that variance of a portfolio needs to not just consider what the individual variances of the individual assets are, but it also needs to consider how the assets vary against each other. So this is where we come across our measures again. We're going to use our measures that we've already met that look at how assets vary relative to each other, things like covariance and correlation. So this is the variance of a 2-asset portfolio, this equation here. It's a little bit of an ugly one to just see straight off the bat like that. So how might we prompt ourselves to remember this formula? Well, I always think, well, look, variance is squared distance, isn't it? So this is why understanding what you're doing is very important, you know, rather than just using the calculator. So variance is really an average squared distance, isn't it? All right, so it's based on squared distances. So you can think of it as an average squared deviation from the mean, or squared distance. So if you were to if you had a portfolio and you had weight A, and asset A had standard deviation of sigma A, and then you combine that with an asset of asset B with a weight of WB and a standard deviation of sigma B, I always think that variance is going to be related to what happens when you square this, not just that straightforward addition itself. Now, if we go back to school, when you square these brackets out, and we go back to, you know, elementary sort of maths at school, when you square those brackets out, what happens? Well, you multiply the first term together, right? So you get a squared term for the first term, WA squared, sigma A squared. Great. And then what you do is you multiply the first term by the second term and the second term by the first term. So you get this kind of 2 lots of WA, WB, sigma A, sigma B. All right, and I'm going to leave a little blank there. and then you multiply the final term together, so you get a squared term for the final, for the other asset, asset B. Okay, now you've nearly got the formula for portfolio variance. You nearly have, just by thinking about squaring out these brackets. I think a very intuitive way of looking at it. All right, I mean, it's not a formal way of looking at it, but we don't need to formally derive this. We just need to have a hook to take the to take the sting out of this formula. The gap that I've left here is actually the correlation coefficient between asset A and asset B. You might remember the correlation coefficient gets the letter R for a sample. It gets the letter Greek rho, curly P, a Greek rho, when we're looking at true correlation coefficient. So that's your correlation of A and B. Okay, so me just putting that correlation in there, that's where we are reflecting how assets A and B behave relative to each other. And that's it, actually. That is a version of the two asset variance formula. If we go back to the slide, you'll see that version sitting at the bottom of the slide that we just left. So there it is there. All right. Now we haven't derived it, but we've shown a good way of kind of interpreting it. Using it is more important. We don't need to derive it. Now there is a super important relationship that we can use to get from correlation, that's correlation there, to get from correlation to covariance. You need to have this on board for the exam. All right. You need to recall that correlation, so that curly P, that rho is correlation, remember. Correlation of two assets is equal to the covariance of the two assets. It's standardized covariance, isn't it? We did discuss this earlier in an earlier module. So take your covariance, divide through by standard deviation in asset A, standard deviation in asset B, and you'll get to correlation. All right. You might sort of say, well, where does this come from? We did discuss this before, and this is super important. All right. Super important that you have this relationship on board. And it's also super important that you can rearrange this relationship and say, well, in that case, the covariance of two assets can be viewed as sigma A, sigma B, correlation AB, right? If I multiply both sides by sigma A, sigma B, that disappears, but then it pops up on the other side next to the correlation coefficient, and I've just switched it around. So covariance can be expressed as the product of standard deviation and correlation. Don't forget, once again, that curly P, that rho is correlation. Okay, so with that in mind, we look at that bottom equation on the slide and we realize that what we're looking at here, in other words, correlation and the product of standard deviations, what we're looking at here is actually the covariance of the two assets. So you could have just written covariance times WA/WB for that, what's called a cross product term. So you either like that kind of discussion and it gives some color to it, or you don't like it and you kind of go, I'm just going to remember it. Okay, if you're just going to remember it, go for a squared term for the first asset, squared term for the second asset, and not a squared term, but an A and B cross term. There's two of them because you can combine A with B and B with A, two lots of WA, WB, and then the covariance. And make sure you can expand covariance into this expression and use correlation if you're given it. So that's the case for two assets. What we're going to do next actually is we're going to apply this idea for three assets. So we might need to just think briefly about what happens when we have a three asset portfolio. We've already seen that with two assets, our portfolio variance is, and I work in covariance terms, is squared term for the first asset, squared term for the second asset, plus two lots of WA, WB covariance, AB. All right, now if you expand this for three assets, what are you going to need to add? Certainly you're going to need to add a squared term for the third asset, so WC sigma C squared, so WC squared sigma C squared, that squared term, all right? And what else are you going to need to add? You're going to need to add these cross terms, this term that looks at how two assets behave relative to each other. You're going to need to add actually two of these, aren't you? You're going to need to add one for how A interacts with C, the new one we've added, and you're going to need to add one for how asset B interacts with the new asset C. Okay, so notice that this is not a it's not a straightforward idea, this portfolio variance. When you add one more asset, it leads to 1, 2, 3 more terms. And that's one of the problems of this approach, is the number of estimates you need as you scale up the number of assets in your portfolio. It actually goes up by a factor of the square of the number of assets in your portfolio, rather than just being directly related to the number of assets in your portfolio. But more on that when we get into portfolio management later on. Okay, by the way, returns are always behaving themselves, aren't they? So when we think about a 3-asset portfolio, when it comes to returns, it's nice and straightforward. You would guess, wouldn't you, that the expected return is just weight of the first asset times return of the first asset plus weight of the second asset times return of the second asset plus weight of the third asset times return of the third asset. Like I said at the start, these returns always behave themselves. It's the variances that cause trouble in the calculation. And also, don't forget, if you're asked about standard deviation, don't forget to square root variance as well to get back to standard deviation. That's often kind of like a bit of a tragic thing to forget at the end of all of this. So let's have a look at a CFA Institute example here. We've got 3 assets here, so we're going to go for the big one, the 3-asset one, straight away. Here are your weights. If you called these A, B, and C, you can kind of map them to the formulae that we've got. That must be WA, WB, WC. And here's our expected returns. So, like I just said, the expected return of the portfolio is not a troublemaker at all. Weight of asset A times return of asset A plus weighted return of asset B plus weighted return of asset C, and we are done relatively quickly. So that's good. We know the troublemaker is variance. That's where we need to tread a little bit carefully. So when we think about variance, you already know we're going to need to know the variance of the individual assets. We're also going to need to know how they co-vary against each other. So this is where we come across our first variance covariance matrix. What this is showing us, if we kind of generalize and call these assets A, B, and C, what it's showing us is the rows relate to the 3 assets and the columns do as well. And so in the table, what we're looking at is the covariance of the asset in the row versus the asset in the column. So for example, this one here, 45, is the covariance of A versus B. Notice that that's the same as the covariance of B versus A. All right, so this is a symmetrical table about the diagonal. All right, this must be the covariance of C versus A, which is the same as the covariance of A versus C. And this here must be the covariance of C versus B. Okay. Because it's symmetrical, you're often only given one side of the table. Right? You might only be given the bottom diagonal, and the top diagonal could be left blank. All right, on the assumption that, and it often is, on the assumption that you can just say that the other side is you can see what the other side is because it's a symmetrical table essentially. Okay. However, the diagonal is very interesting. This diagonal here, that must be the covariance of A versus itself. Now, the covariance of A versus itself, sounds quite strange because it's more commonly referred to as the variance of A. If you think about it, the variance of A is how far A is away from its mean squared, which is how A covaries with itself. How far away from the mean A is multiplied by how far away from the mean A is. That's the deviation of A squared. And if you take the average deviation of A squared, you're looking at variance. So the key takeaway here is that the diagonal gives you variances. That's why it's called a variance covariance matrix. So that's the variance of A, that's the variance of B, and that's the variance of C. All right. So now we've got all the ingredients. Don't forget, when we talk about weights, the weight of A was 0.5, the weight of B was 0.25, and the weight of C was 0.25. So now we've got our ingredients, we know our recipe, the formula recipe, so we can just plug and play. All right, this term here must be WA squared sigma A squared from the table. All right, it's coming from here, WA squared sigma A squared. This is WB squared sigma B squared. All right, going down the diagonal here, and this is WC squared sigma C squared. Okay, and then you've got your cross product terms. This must be WA, 2 lots of WA. That's probably WB. Yeah, it is WB because that's the covariance of A and B, or B and A, same thing, right? 45. This one here is the cross product term for A and C, yeah, because you know the 189 is how A and C vary against each other. And this is the cross product term for B versus C. 2 lots of WB, WC, and then covariance of B and C, 38. Now, if your calculator's in the right mode, you can just punch that through. You can go 0.5 squared times 400 plus. It will do the square first, do the multiplication second, and it will do the plus last, which is what you want to happen. So that's an example of where your calculator being in that AOS mode that we've spoken about a couple of times now. Go and see previous module videos to address that. That's where that speeds you up quite a bit. Now be careful, this is portfolio variance, all right? It would be a bit of a tragic mistake to say that that's the portfolio standard deviation. It's not, of course. Standard deviation is the square root of variance. So if we take the square root of 195.875, we get back to 14-ish, or close enough to 14. Now here's an important point about this table, and don't forget this table's come straight out of the curriculum. These numbers in here, they are percent squared, whole percent squared, okay? How do I know that? I know that because they're large whole numbers, all right? The fact that sigma A squared is 400, that means that sigma A, and we are looking at the S&P 500 here, sigma A is the square root of 400, right, which is 20. Now, look, that thing is percent volatility, okay? That's the original units of returns. So, it can only make sense that that 20 that we started off here and squared to get 400 is in whole percent terms. Otherwise, if that's a decimal, then, you're looking at a volatility of, 200%? So it's 100%, or is it 2,000%? Yeah, it's 2,000%, isn't it? Which is crazy volatility for the S&P 500. You might be concerned that you won't be able to distinguish in the exam. The best piece of advice I could give you really is that the Institute goes with whole percentages here, right? So the numbers come out nice and big. If they'd gone with decimals, like if they'd gone with, say, we're going to be, and it's actually technically more correct, but if they'd gone with decimals and they say sigma A is actually 20%, which in decimal terms is 0.2, then they would have got sigma squared A of 0.2 squared, all right? So this is where you're going to see small numbers. We know there's a 4 in it, all right? It would be 0.04, all right? And you'll start to see very small numbers, okay? So if the numbers in this table were very small, lots of 0.0 and 0.00, this and that, you're using decimals. If the numbers are big and round, then you're using whole percentages. So given the curriculum uses whole percentages when they present this information, as we're seeing here, I would suggest you assume they're going to use whole percentages in the exam. So when you take a square root here, what you're actually getting back to is a 14% whole percentage. Okay, why? Because those numbers that we're using were squared whole percentages essentially to begin with. Okay, next up, we're going to calculate the covariance of a portfolio in a slightly different way. We're going to calculate it based on joint probabilities of what the assets could do in the portfolio. Now, as I said in the intro, a joint probability, we've already discussed it when we were talking about Bayes' formula and things like that. A joint probability is the probability of two things happening at once. It's an AND probability. All right. So when you get given a joint probability table like this, what you're actually looking at in this cell is the probability that asset A returns 25% and asset B returns 20%. Okay. You'll notice that they've left the rest of this table blank, and this is really for ease of calculation. So I wouldn't expect them to mix this up and make it more complicated. Really what they're saying is there's only three things that can happen. Notice that diagonal does add up to 100% or 1. There's only three things that can happen. A could take a return of 25% and B would be 20, definitely in that case. And if A is 12%, then we know B is at 16. And if A is at 10%, then we know B is at 10% also. Now what you can do to calculate expected returns and covariances, one of the first things you can do is calculate the expected returns of the assets. If we just focus on asset A, there's only three returns it can take. This one, and this one. And the probability of those three returns, technically it would be the sum of the rows, all right? Technically, if there are any non-zero values, you take the sum of that row. That would be the unconditional probability of A taking 25%. But given there's only the diagonal here, we know we're going to have the sum of the row being 0.2, some of that row being 0.5, some of that row being 0.3. So hopefully it's relatively straightforward. To get the expected return of asset B, you're going to do a similar approach, but just think about what you're doing. With asset B, it could take values of 20, all right, and 16 and 10, and actually the probabilities here will be the sum of the columns. They're the same numbers, but if there were any non-zero probabilities off of the diagonal, technically what you're looking at here is the sum of the columns, giving you the probability that B takes 20% or 16% or 10%. Okay, and that turns out to be 15. Now you can see how ugly the covariance formula is here. Look at this, a double summation sign. You know, I've got a little bit of history with maths myself, and even I kind of see double summation signs and I think they're not doing much. You know, they're doing more harm than good, right? They mean, of course, sum over both A and B, right, in 2 dimensions. But what we're going to do is I wouldn't worry about learning that. What we need to do is apply it. Now, this is where understanding comes in. Covariance is, what is it? Can you answer that in words, right, without a formula? That's the most important thing to be able to do. What it is it's your average or your expected joint deviation from a mean, all right? Looks like there should be a bracket there, okay? So what we're going to do is we're going to go through this table, and at each cell, really, there's lots of 0 cells, so we don't need to worry about them. They can't happen because they're the probabilities in the table, all right? But for each cell, we're going to think, what's the probability of being there, and how far away is A from its mean for that cell, for that row, essentially, and how far away is B from its mean for that, for that cell, for the column, essentially. All right, we know what the means are. We've just calculated them, 14 and 15. So it's actually relatively straightforward. All right, what you're going to do is you're going to say, look, my covariance is there's a 0.2 chance that I observe this cell. All right, think of it like a cell in a spreadsheet. And in that cell, A is this far away from its mean of 14, and B is this far away from its mean of 15. Okay, the 2 numbers we just calculated. Then there's zeros here, so we don't need to worry about the off diagonals. There's a 0.5 chance we end up in that middle cell, and that's what A is doing in the middle cell, and that's what B is doing in the middle cell, and that's how far they are away from their means. And similarly for the final non-zero cell. Okay, obviously if there are non-zero probabilities, it becomes a lot more complex. You just go through the table and have to use the values for A and B relevant for that cell. Think about how far they are away from their means. But this is how the CFA curriculum presents it. You're done here. We've used whole percentages here, so we've come out with 16. More precisely, if decimals returns have been used, if decimal returns have been used, you're going to be multiplying together 2 things that are 100 times smaller. All right, so if you are making things 100 times smaller twice because you're multiplying through by something that's 100 times smaller twice, if you use decimals, then you're going to divide by 100 squared. So you'd have got 0.0016. Once again, that ties into a conversation we had earlier on, and that is, if you use whole percentages, you'll get big numbers. If you use decimals, you'll find lots of numbers that begin 0.0 and 0.00, okay? Because the difference between them is a factor of 100 squared. Right, on now to the last area in this particular module, and a very, very, very important area for not just your CFA level 1, but your CFA overall. And if you're working in finance and you want to understand what any statistician says about anything, you need to understand the normal distribution. So the normal distribution, we have met it before in a previous module, but we're going to formally reintroduce ourselves to it and use it this time. That's what the difference is. You'll remember that a normal distribution, it's the old famous bell curve. It has got a mathematical function to it, and the mathmos will be using that, but we don't care about the mathematical function. What we care about is that we want to use it. It does beg the question, why do people use it so much? Well, actually, we've found empirically that when you have lots of random forces acting on a particular variable, what you tend to find is that we're very closely clustered around the mean, and as we move away from the mean, we tend to see fewer observations, and that's what this probability distribution is showing you. Remember, you can view the y-axis as kind of like likelihood of being in that area, all right? So we're very likely to be around the mean, and the further we move away from the mean, the less likely are we're going to observe a value out there. Mu for mean here, All right. If you've got the mean of the distribution, that gives you its middle, the middle of the bell. And if you've got the variance or the standard deviation, don't forget standard deviation is the square root of variance, then you've got the width of the bell, and therefore you can define the bell. Like I say, you're not going to use a mathematical equation, but what you are going to do is apply known facts about a normal distribution. All right, just to repeat something we saw in a previous module, we know it's symmetrical. That's often problematic when we're modeling financial assets that have negative skew. All right, so skewness is 0. This is kind of a simplifying assumption. And kurtosis, that's your average deviation to the power of 4, describing the shape of the bell, is 3. Don't forget that excess kurtosis, which is how much kurtosis we have relative to the normal distribution, is 3 minus 3, which is 0 for the normal distribution. Don't forget leptokurtosis is high kurtosis, and that's kurtosis greater than 3, or positive excess kurtosis. And that's what we're worried about in financial markets, because it means high kurtosis means we've got fat tails. Okay, fat tails. Just a bit of revision here. Fat tails. We are more peaked, but it's the fat tails that we're worried about because there's more chance of an outlier. That should be symmetrical, of course. That's a high a high leptokurtic distribution there. Okay. All right. Now going back to the normal distribution, we're going to use it. Any normal distribution with any mean and any standard deviation or variance, right? We know we can make statements about how far you need to go away from the central mean. All right, so there's the mean there, the expected value. We know we can make statements about how far you need to go to observe a certain proportion of the population. With these probability distributions, it's actually area under the curve which represents probabilities. That's why I describe it as a likelihood function, not actually probability itself. So that's a bit naughty, having probability on the axis there. It's actually the area under the curve that represents probability. All right, that's why they're called probability density functions. How much density have we got here? So it's the area under the curve. And what we see is that if you go one standard deviation to the left of the mean and one standard deviation to the right of the mean, you create a range which captures about 2/3 of the distribution. It's actually 68%. Okay, that's true of all normal distributions. This is what you need to realize, is that as soon as we assume something's normal or we find something that's relatively normal, we know a lot about the ranges that we need to go to capture a certain proportion of the population, and we use that a lot. If we want to be 68% confident that we've got a range where we'll see the next observation coming out of a return distribution, if we assume it's normal, then we know what range to calculate now. That's what we're going to do. Okay. Incidentally, if you go 2 standard deviations away from a normal mean, you will capture about 95%. That's approximately 95% of the distribution. It's worth, the exact value to capture 95% of the distribution is actually 1.96, which is approximately 2. Okay, this slide is making that approximation. Now it's worth just pausing here for a moment. This is real fundamental core stuff. We don't want to lose people here. It's worth just pausing for a minute and thinking about a different way of coming at this. So what we've just said here is for any normal distribution, I haven't specified what the mean is and what the standard deviation actually, what they are. Right now that should be a nice bell curve, but I haven't drawn it massively well. The mean is in the middle, don't care necessarily what it is. Standard deviation, we know it, but don't necessarily care exactly what it is. What we're saying is, in general, if you go 2 standard deviations away from the mean, all right, you will capture 95%, about 95% of the distribution. Okay, now here comes the important point. What does that mean the area in each tail is? Well, the area under the curve, the whole curve is 100%, because you've got to observe something somewhere. Don't forget, area under the curve is probability. The fact that we observe something somewhere, if we're taking a reading, is 100%. Okay, so if it's symmetrical, which it is, we've got 2.5% in this tail here, and we've got 2.5% in this tail here. Okay, the way to do it is you just obviously take 100 minus 95, the area under the bell, and you divide it by 2. Okay, so here comes a really crucial point. This distance of about 2 standard deviations, it's actually, to be exact, it's actually 1.96 standard deviations. This distance of 1.96 standard deviations, to be exact, It's about 2. 2 will do usually. But exactly, it's 1.96. If you go that far away from a normal mean, you will isolate 2.5% in the tail outside it. Okay? All right, and that's the way to think about these distances. How much of the distribution does it isolate outside of it? Then if you've got 2 tails, which we have in this analysis, you can say, oh, okay, if I go 196 that way and isolate 2.5, and I go 1.96 that way and I isolate 2.5, then what I'm actually isolating in the tails is 5 in total with 2 tails, therefore there's 95 under the bell. Now, I'm not spending a lot of time here for fun. You can tell that, right? Because this isn't really that much fun. I'm spending a lot of time here because I know like the top 3 mistakes and speed bumps and pitfalls and mine shafts and, you know, cowpats that people fall down and tread in when they're doing their CFA level 1. And this is one of them. This idea that you can look at the confidence and you know what the distance is. Actually, you can look at the confidence and know the number of tails. Confidence is the area under the bell, by the way. All right, just to give it a bit of jargon. You know, we're 95% confident we'll observe something in this range for this distribution. Okay. The mistake is that people look at confidence and they go, 1.96 for 95%. But you go, hold on. What about if I was looking for a level where I want to be 95% confident I'm greater than just one tail, right? So there's 5% in that tail there. Now what's the distance? 5% in the tail. It's not going to be nearly 2 standard deviations, is it? It's going to be less than that because it's not going as far, right? So always think about the area in the tail. By the way, just to spoil it, to isolate 5% in a tail, you would have to go 1.65 standard deviations to the left or the right of a mean. And by the way, if you go 1.65 standard deviations both sides of the mean, all right, then what are you capturing under the bell? What's your confidence that you're capturing here? Well, with 1.65 either side, you're isolating 5% each side, right? So actually there's 90% under the bell here. So this, this is why I keep saying focus on the area in the tail and be very aware how many tails you've got. Otherwise, you are going to make the classic mistake here. Okay? All right, with that in mind, here's a summary of key distances for your level 1 that you need to know for the normal distribution. Okay? If you want to isolate 5% in one tail, we've just said 1.65 standard deviations will do it. All right? And that will isolate 5% in one tail. Incidentally, if you've got 2 tails, as I've just said, it will capture 90% of the distribution because 100 minus 2 lots of 5 is 90. We've also said 2 will do to capture 95%. All right, that was a 2-tailed comment, wasn't it? All right, you actually isolate 2.5% in each tail if you go about 2 standard deviations either side of the mean. Okay, so be careful. Always focus on the area in a single tail, and then you can decide, to adjust if there's 2 tails in play. 2.33, that's how far you need to go to isolate 1% in a single tail. 2.33 standard deviations. And 2.58 standard deviations, that's how much you need to go to isolate 0.5% in a tail. So, we haven't drawn these and discussed these in detail, but basically if you go 2.33 standard deviations away from a normal mean, there's only 1% left in the tail. So, you're 99% confident that you'll do better than that as a single tail observation. If you're using it in both tails, then of course you're going 2.33 standard deviations either way, and you're isolating 1% in each tail. So under the bell, you're creating a confidence interval here where you've got confidence of 98% if there's 2 tails. And a similar analysis for 2.58. Isolate 0.5% in one tail, which is not common because you're 99.5% confident you'll beat it or you won't beat it depending which tail you're looking at. But this is the most common one. If you go 2.58 standard deviations away from a mean, so 2.58 standard deviations away from a normal mean, you will isolate 0.5% in each tail, and therefore there's 99% under the bell. And these are common confidence levels used in statistics, and indeed they're going to be used quite a lot, not just for the rest of level 1 when we get into proper statistics later on, but level 2 as well. Okay, so let's make sure we can actually calculate these confidence intervals. I've been talking a lot about generalizing distant in terms of distances, but let's make sure we can calculate one. We know that 90% confidence interval 1.65. That's people often say, do I need to learn these for the exam? And my answer, the short answer is, yeah, go on. But what about would they give it? And the short answer is learn them. Yeah. Okay. So isolating 5% in a tail, you go 1.65 standard deviations there. Okay. And once you go 1.65 standard deviations, you capture 90%. That's really isolating 5% in each tail. You know that, right? From the previous table. That's the way I think about it. I always think about the area in the tail. 1.96 standard deviations, you isolate 2.5% in each tail. It's 2 tails, so you've got 95% under the bell. And then as we've just discussed, 2.58 is actually a 99% two-tailed confidence interval. Okay? All right, so let's do it. Let's put some numbers in. The mean annual return, which is normally distributed, or at least assumed to be, on a portfolio is estimated to be 11, so that's your mu. That goes in the middle here. And with a standard deviation of 8, so that's your sigma. That's the dispersion of the distribution. Calculate a 95% confidence interval for the next year's returns, for the next observation. Now, 95%, I would always tread really carefully, particularly if you are, particularly if you're coming across this for the first time. To get a confidence interval around the mean, you're going to go to the left and to the right. Okay, so these confidence intervals are always two-tailed. Okay. In other words, you're going to go to the left a certain distance, and you're going to go to the right. I do know my rights from my lefts, honest. So you're going to go to the right a certain distance and to the left a certain distance, and you're going to isolate in the tail 2 areas such that there's 95 under the bell. That's what we mean by confidence, and therefore there's 5 in both tails. There's 2.5 in each tail. All right, so look, by this stage you should be thinking 95, 2 will do. Technically it's 1.96. Okay, so we'll start at 11, and they write this in the text as plus/minus because you're going to go each way. We're going to add 1.96 times standard deviation of 8, and we're going to subtract 1.96 times a standard deviation of 8. Right, so just to interpret what's actually being said there, because that's slightly odd when you see it first time, the 1.96 standard deviations here is 1.96 times 8, we're working whole percent, 15.68. So you're going to go that either side of a mean of 11, all right? So, if we call it 15.7, shall we, to round it a bit, you can see we're going 11 minus 15.7 is minus 4.7, and 11 plus 15.7 is 26.7. That is the range where you are 95% confident you're going to observe the next return. Otherwise, something very unlikely is happening. I mean, it could happen, but it's very unlikely. It's only 5% likely. Okay. All right, so there's the slide animation doing what we've just said. Okay. Okay, what we're going to do now is we're going to just introduce a little bit of formal terminology for these distances, because I keep calling them a distance, the number of standard deviations you need to go away from mean to capture a certain proportion, or to isolate, more usefully, to isolate a certain area in the tail. The formal name for these distances is a Z value. All right, that's the formal name for these distances. If you think about what these distances actually are, these distances, in terms of the number of standard deviations we need to go to capture, a certain confidence level, a certain percent. These distances are referred to as Z values. If you think about what these distances actually are, they're really for a given value that we're interested in. How far away from the mean are we? So this is a value X. These are values for return, something like that. X is just a random value. We've got a mu here in the middle, a normal bell curve there. All right. Let's say that X is here. We're interested in the distance of X away from mean in terms of standard deviations, right? We're interested in X's Z value essentially. So what we're going to do is take the absolute distance, X minus mu. So that's on the numerator there. And we're going to divide by 1 standard deviation. All right. And that will give us the number of standard deviations that X is away from mu. All right. So that's a more formal and a more general way of calculating these distances. We've looked at some key distances. For example, a key distance of 1.65 to isolate 5% in the tail. We've looked at some key distances, but more generally, for any observation, X, from a normally distributed, any value essentially from a normally distributed distribution, a normally distributed variable, you can calculate the distance away from the mean in terms of standard errors, which is called a z-value as follows. You might beg the question why they're called z-values, and the answer to that is that what you're really doing, technically what you're doing is you're transforming your original distribution. By subtracting mu, you're shifting its mean to be 0, and by dividing through by the standard deviation of the original distribution, you're turning the standard deviation of the distribution into 1. So this z-value can be interpreted as being a very special type of normal distribution, and that's what's referred to as a standard normal distribution that's got a mean of 0 and a standard deviation of 1. So there's two different ways of interpreting the z-value. Formally, a z-value is a standard normal distribution. That word standard is telling you it's got a mean of 0 and a standard deviation of 1, and we're transforming any other normal distribution onto that when we do this calculation. That's the kind of technical point. The non-technical, more practical and useful way of interpreting this z-value is that it's a distance away from a mean, okay? In terms of standard deviations, okay? Let's use it. Have a look at this. You can, by the way, given a z-value, now this is an important juncture. Something we're going to be doing a lot is we're going to be calculating z-values. This is something that you might find yourself doing a lot. If you need probabilities when you're dealing with a normal distribution, all right? Like what's the probability of observing more of a value or less of a particular value, some sort of value for X, yeah? Then what you're going to do is, number one, take your value and standardize it, all right? So calculate how many standard deviations you are away from the mean, okay? Calculate the Z value for what you're observing. And then number two, you're going to use what's called Z tables to get probabilities of your observation being, say, less than that, and then you can derive what the probability is being greater than that, all right? So the idea is these Z tables, they are tables which you put a Z value into and out comes a probability, right? For these Z tables relate to the standard normal distribution, that single distribution with a mean of 0, standard deviation of 1. We can just create a table for that, and we're really mapping all other types of distribution that we look at onto it. So by doing this Z value analysis, put a Z value into the table and out comes a probability, all right? I'll show you, it's this process, I'm going to demonstrate it rather than describe it. That'd be better. Have a look at this. So I've been discussing this Z table idea. It gives us probabilities. Technically, they're cumulative probabilities. That's the probability of being less than a certain value, all right? Like being in the tail. Gives us the cumulative probability. The probability that we're less than a certain Z value is the area outside of the Z if it's a negative Z to the left, all right? For the standard normal distribution. And we can use it, it's very useful. We put a Z value in, don't forget, and we get a probability out of the table, okay? So have a look at this. The EPS for a large group of firms is normally distributed, has a mean of $4 and a standard deviation of $1.50. Find the probability that a randomly selected firm's earnings are less than $3.70. Now, I would always recommend drawing stuff to help you picture what's going on. Otherwise, you can get stuck very easily. So as soon as somebody says normal, a normal distribution, you can kind of go, all right, fine. So the distribution I'm looking at is normal. It's a bell curve, right? It looks a bit like that. The mean is in the middle, so the mean is 4, and the standard deviation is $1.50. Okay, that's the width of the bell. Okay, we need to find the probability that a randomly selected firm from this distribution has earnings less than $3.70. Well, $3.70 is here. All right, that's where $3.70 is. Okay, it's less than 4, obviously. And I need to find the area in that tail. Now, that's what a Z table tells you. It tells you the probability of being less than a certain Z value, in other words, being in a tail. Now, in terms of what you need to do, you need to use, don't forget our steps here, we need to use Z values to get probabilities. So we're going to have to calculate the Z distance that's relevant for our observation. All right, so what do I mean by that? Well, our observation that we're interested in is 370. If you like, that's our X term. All right. What we need to understand is how far away is that 370 from the mean of 4 in terms of standard deviations of $1.50. So that's us calculating a Z value. To do that, $3.70, what we're interested in, minus the mu of 4. That's negative 0.3, of course, but that's not interesting. What's more interesting is how many standard deviations is that. So we divide by sigma, and we get to negative 0.2 standard deviations. Right, so, that sigma there is a little bit of imposter. I'd prefer not to see that there because it suggests it's 0.2 times sigma. Sigma is 1 for the standard normal distribution, so technically that's right. But I'm going to just cover that up because what we've got here is a standardized distance. We are looking at negative 0.2 standard deviations to the left of the mean. Now, given a Z table, it's a very peculiar way of using a Z table. You've got your tens, in terms of decimal places, you've got your tens in these columns here, and you've got your hundredths in the rows, all right? So when I see a Z value of minus 0.2, what I know is that this distance here is negative 0.2. That's my Z value associated with 3.7. And what I can do is put that minus 0.20 into the Z table. All right, so this figure of minus 0.20, my Z's are negative here, so that's nice and easy. I've got 2/10 negative, so that's this row, right? And I've got 0 hundredths, so that's this column. Okay, so where this column and row intersect, i.e. there, that 0.4207, that's the probability of being in the tail, being less than, right? That's what a cumulative distribution, cumulative probability is. It is telling you the probability of being less than a certain value. All right. So we've answered the question there. 0.4207 is the probability of observing a return less than 3.7. We answered it using Z values, but it pertains exactly to our original normal distribution just as much as it does to those Z value distances. Okay, so that's the answer to that question. All right, there's a 42.07 probability that the EPS of a randomly selected firm will be less than the value $3.70. All right, and that graphic there is really summarizing what we said, what we drew on the previous slide. Okay, the applications so far haven't been massively financial. Let's look at some specific kind of financial applications here. We could specify a target return, assume things are normal, and then calculate the probability of having a return less than that target return. It's a risk measure. It's called shortfall risk. Okay, so using this kind of error in the tail approach, we could have a target return and use our Z values and Z tables to calculate the area outside that target, which would be the probability of missing the target. Yeah. In terms of distances, we could calculate Roy's safety first ratio, often abbreviated to SFR, safety first ratio. This is just telling us for a given portfolio with a given mean and a given target, which in this case is described as a minimum acceptable return. All right, usually we're thinking about this distance here in terms of standard deviations. It's really just a Z value. Roy's safety first measure is a Z value for this target versus a mean. A Z value, don't forget, is distance in terms of standard deviations. So you can see it's how far the mean of the portfolio is away from the target. So that RL there is the target of the threshold return. So L for, if you like, a limit that we need to meet, all right, or least return that we want. Think of it as a threshold or target. this is just a Z value, isn't it? Thinking about what our distance is in terms of standard deviations. It's a Z value. It doesn't reflect signs though, because it's flipped around the numerator, but it's really just a Z value. Incidentally, if the target is the risk-free rate, what we're actually looking at here with the safety first ratio, SF or SFR as I've seen it in the text, is the same as the Sharpe ratio, because the Sharpe ratio is defined. All right, it's probably worth defining the Sharpe ratio before we just start talking about it. It is something that's spoken about a lot in portfolio management. The Sharpe ratio of any investment is how much the investment is expected to outperform the risk-free rate per unit of risk. All right, that's the Sharpe ratio, and the higher the Sharpe ratio, the better. If your target is the risk-free rate, then this safety first ratio becomes the Sharpe ratio, which is the same as the Sharpe ratio. And generally, this idea that the higher the better comes through as well. The further you are, because this is really just a distance, yeah? The further you are away from a minimum threshold return, like a least acceptable return, the better. So have a look at this. Which of the following portfolios has the lowest probability of earning less than 2%? That's good news, isn't it? A low probability of earning less than 2%. That means there's least area in the tail. Here we've got portfolio 1, portfolio 2, expected annual return. So they're your means, like mean 1, mean 2. And here's your standard deviations, sigma 1, sigma 2. All right. So the safety first ratio for the first portfolio is how far our expected return is. So that's the mean, minus the target return, threshold return. That must be RL here. All right, in terms of standard deviation. All right, standard deviation of asset 1 is 15. So that's 0.667 standard deviations away. Seems like a long way away being 10% here, but it's quite a highly volatile environment. What about the other portfolio? The other portfolio is further away. It's actually more volatile, but it's not so much more volatile. The extra distance doesn't count. That is a better safety first ratio. That's the biggest distance away from that minimum acceptable return of 2%, and therefore will have the lowest probability of being in the tail. If you try and picture what's going on, we've got, if you like, portfolio 1 is only 0.66 standard deviations away from that minimum acceptable return. Portfolio 2 slightly further away, it's 0.75 standard deviations away from that minimum acceptable return, RL. To actually answer the question, what is the probability of being in the tail, all right, that would be your shortfall risk calculation. What we're going to need is we're going to need a Z table, and we're going to need to look up these negative Z values. Technically, these would be negative Z values, okay? So if you're given a Z table extract, incidentally, I should point out that you won't be given Z tables per se in the exam automatically. You'll be given extracts from these statistical tables that you can use should you need them. All right, so you'll be given extracts in the question. So if you're asked about the probability of being in the tail, all right, we know that portfolio 1 had a distance of 0.667 away from the start of the tail, essentially. If we put that Z value, just remind ourselves, the Z value for portfolio 1 is 0.667. That's the size, but actually it's to the left, isn't it? So that would be a negative Z distance. If I put that into this table, let's call it, round it to two figures, so call it minus 0.67. There's 6 tens there, all right, and 7 hundredths. All right, so that row and that column combine to give us that 0.2514 there. That is the probability of actually missing the target. All right, don't forget that this start of the tail here is defined by a return of 2%. Okay, a minimum acceptable return of 2%. If we do the same for portfolio 2 had a Z distance of 0.75. So to the left of the mean, that would be minus 0.7, this one here, this row here, and minus 0.05 in terms of hundredths, that column there. So we'll come out looking at this number here, 0.2276. So that we didn't need to do that. We deduced that from looking at Roy's safety first. Basically, the highest Roy's safety first will have the lowest chance of being in the tail because you're furthest away in terms of standard deviations away from the minimum acceptable return. However, we're going on here to actually explicitly show using Z tables, which is useful, that there is indeed a lower probability of being in the tail. In other words, not meeting the threshold return for portfolio 2. What we're actually calculating here, of course, is shortfall risk. All right. To really picture what we're calculating, that's what the next slide does. We're saying that for portfolio 1, there is like a 25% chance we could be in the tail. That's a number that came out of the Z table, remember? And for portfolio 2, there's only a 22% chance we'll be in that tail. That's where the tail is defined by that minimum acceptable return of 2%. Just a brief point to help you as you go through the curriculum material. We've been looking at Z tables with negative Z values. All right, so we've been looking at going to the left of a mean. So Z takes a negative value. Z's less than 0. All right, and then we take a certain Z value. You calculate it. It's negative, and you get from the table what the table shows you is the area in the tail. You might see a table with a positive Z value. All right, so you might see a table that's got positive values for Z. All that's happening there is that we're starting at the mean and we're going to the right. It's the same thing in the table. All right, so your Z here is going to be greater than 0. All right, and you're still looking at the area to the left of your Z value. It's just that your Z value is positive. Okay, so just be careful with that. The table still tells you the probability of being less than to the left of this value that you've put in, but you've just got a Z greater than 0 here. All of the slides that we've looked at here have got a Z that's less than 0. There are tables out there that obviously give the right-hand tail where Z is greater than 0. So just bear that in mind. Okay, so some really foundational important stuff here. Make sure you're comfortable with the normal distribution. Make sure you're comfortable with the Z value analysis because we're going to keep using that. That's the most important thing in this particular module is the use of the normal distribution and those Z distances.